So I hope you understand the definition of subspace. A subset that itself is a vector space is called subspace of that vector space. Now let us see what are the examples of subspaces of a vector space. For example, earlier we have seen that set of all polynomials of degree 2 is a subspace of set of all polynomials. Similarly, let me give you a subspace of the second one. What is it? A set of all real valued functions, right? So set of all real valued functions over a field of real numbers is a vector space. Now I would like to take a subset of that real valued functions. Can you give me a subset of real valued functions here? Can someone respond? Set of all rational functions. All right. It means that the output is a rational number. Is that what you mean? Because here I say real valued function, I mean the output is a real number. So rational, you're taking rational valued function. Yeah, that can be seen as a subset of this. That's fine. And if you add two rational valued functions, yeah, definitely output is a rational number. Yeah, that's a good one. So that itself is a vector space. Therefore, it becomes a it becomes a subspace. Good. Can you give me one more? You try to give me an example that you have studied in PUC related to functions. First, you define a function, and thereafter you discussed something about that function, limit, and after limit. What is it you discussed? Hello? You studied continuous functions, right? So you can take set of all continuous functions. Set of all continuous functions is a subset of set of all functions. And you can see that adding two continuous functions will give you a continuous function again. Multiply a continuous function with a constant will give you a continuous function again. And moreover, zero function is continuous, that is constant function. What I mean, suppose if you take a function f, like f of x equal to 0, this is what we call continuous function for every x in the domain. Sorry, this is what we call a zero function. So zero function is a constant function. A constant function is always a continuous function. Okay, so zero is also available. So we can conclude that set of all continuous functions is a subset of this set, and moreover it is a subspace. Not only set of all continuous functions, you can take set of all differentiable functions. Okay, but that itself you can see it as a big set, and if you want you can keep some conditions like set of all continuous functions passing through origin. Okay, so let me give you one interesting example. So u equal to I'd like to take set of all functions u equal to f of x that belongs to c of ab. What I mean, the c of ab, it means this function is continuous on this interval. F is continuous on this interval. And no need to write f of x here. I can simply write f only. This represents a function. U equal to set of all functions which belongs to CAB, a continuous function over an interval a comma b, such that f of a equal to 0. Okay, or if you don't want to restrict to an interval, you do one thing. You take the big set itself. Let f be a function, a real valued function, and continuous, and it passes through origin. But here there is no guarantee that origin 0 lies in this interval. That's why I have taken the point a, f of a equal to 0. Now you do one thing. Try to take two such functions from this. Let's say f, it belongs to u, whereas g also belongs to u. F and g are continuous, and f plus g is also continuous. There is no doubt in it. But we have to verify f plus g, does it satisfy this condition or not? That we have to verify. It means that you know f of a equal to 0, g of a equal to 0. But the question is, how about f plus g? F plus g of a. And we know this one can be written as f of a plus g of a, and individually they become zeros. Therefore, the sum is 0. Therefore, f plus g is also passing through a comma 0. And similarly, you can observe that alpha into f of a, that can be written as alpha into f of a, which is same as alpha into 0. So we'll give you 0 again. So alpha f is also passing through a comma 0, right? And for a 0 function, 0 of a is anyway 0. There is no issue with it. 0 function is available here, right? So the rest of the properties are obvious. So you can say that this is a vector space. So therefore, it is a subset of, it is a subspace of set of all functions. Moreover, it is a subspace of set of all continuous functions on AB. Okay, this is actually, it is coming from a big family, and in this big family again you're considering some other big family in which it is a subset. The first big family is set of all functions, and the second big family is set of all continuous functions, and there is one more big family here, that is set of all continuous functions on an interval AB. Okay, there it is a subset. All right, but remember one thing, if you replace this 0 with some non-zero entry, then it is not going to be a vector space. Why? Because suppose if I replace 1 here, f of a is 1, g of a is 1, f of a plus g of a, 1 plus 1, you'll get 2. You don't get 1 again. So it cannot be a vector space. Okay. All right. So similarly, you do one thing. Your exercise is to think set of all subspaces of m by n matrices. Okay, suppose if it is a square matrix, you know there are many subsets for a square matrix. For example, symmetric matrices, skew symmetric matrices, nilpotent matrices, or set of all matrices whose trace is 0. These are all subsets of square matrices. Check which of them are vector spaces. If they are vector spaces, then you can say that those are subspaces of the matrix space. Okay. And you think for some examples on it, and you better bring those examples to the classroom. All right. And next, for set of all real valued sequences, you can take set of all sequences converges to 0. Set of all sequences converges to 0. If one sequence converges to 0, other converges to 0, their sum also converges to 0. All right. Now let me do one thing. Let me start giving you a subspaces of these spaces. Those are R2, R3, Rn. And the beauty here is you can see them geometrically. Okay. So let me start begin by giving subspaces of R2. But before that, let me talk about R itself. Okay. Now this is the vector space I'm taking. V equal to R, and the field is also R. It means I'm talking about this vector space R over R. Right. Now can you give me a subspace of this vector space? It means, can you think of a subset of real numbers that becomes a vector space? I want the proper subset. Why? Because R itself can be seen as a subset of R, but it is an improper subset. But I need a proper subset. Is it possible to find a subset of R that becomes a vector space? So if you take just 0, I mean, U equal to, that is a set which contains only 0, a singleton set. Now this becomes a vector space. Why? Because if you add two elements here, the resultant is there. Two elements add చేయడానికి అక్కడ ఉంది ఒకలే. 0 ని 2 times add చేయాలి. If you add 0 2 times, again you'll get 0. And if you multiply a 0 with any real number, you'll get 0 again. It is there in the set itself, right? And rest of the properties, like related to addition and multiplication, they were anyway true for the big set. If they are true for the big set, definitely they will be true for the small set also. What I mean, associative property holds for every element in the big set. You pick up any three elements from this set. For these three elements, associative property holds. If it is true for every three elements in this set, definitely it is going to be true for every three elements in the small set also. Because you're just looking at the addition, some like a1 plus a2 plus a3, right, which is equal to a1 plus a2 plus a3. We know that this property holds for every three elements in V, right? So similarly, if you take some elements in U, those are elements of V, and we know for every element of V it is satisfied. Therefore, for every element of U also it is satisfied. Are you getting it? So to check whether a set is a subspace or not, it is enough to check only two conditions. One is the addition and the scalar multiplication. No need to worry about those associativity, commutativity properties. Why? Because in the bigger set, they satisfied, right? So for the smaller set also, it happens. Why? Because those are just operations. Okay. All right. So now 0 is one set that becomes a vector space here. Now, are there any other vector spaces? I mean, are there any other subspaces of R, subset of R, which becomes a subspace? You have the entire real line on which you found just only one element, one subset, that is 0 subset. All right. Other than this, do you have any? ఇంకా సబ్సెట్స్ ఆఫ్ రియల్ నెంబర్స్ అంటే అవి సింగిల్టన్స్ అయి ఉండొచ్చు. ఇప్పుడు సింగిల్టన్ 0 మాత్రమే అవుతుంది ఇక్కడ. Let me ask this question. Suppose if u equal to -1 to +1 closed interval, right? Can it be a subspace of R? All right. So the field is real numbers here. So I have to take real number field only, because whatever field you have it for the bigger set, the same field we have to take it here, right? So now if you take a real number and multiply with a number here, that may not lie here. For example, 2 into 1, that doesn't that doesn't belongs to u. Therefore, it cannot be a vector space from that way. And that is one way. And the other way is you take two elements here and you add it. For example, if I take 0.9 and 0.8, right? So if I add it, the result is 1.7. It doesn't belongs to you. Even addition also not satisfied. Not only that, multiplication. So adding two elements here does not belongs to you. I found two elements such that adding of them does not belongs to you. There may be some elements in it, like if you add those two, they stay in u only. For example, if you take 0.5 and 0.4, if you add it, the result is 0.9. ఇప్పుడు కొన్ని ఎలిమెంట్స్ కి సాటిస్ఫై అయితే సరిపోదండి, అన్ని ఎలిమెంట్స్ కూడా ఇది సాటిస్ఫై అవ్వాలి. ఏ టూ ఎలిమెంట్స్ యాడ్ చేసినా సరే రిజల్ట్ దాంట్లో ఉండాలి. ఏ ఒక్క రెండు ఎలిమెంట్స్ ఫెయిల్ అయినా we say it is not a vector space. Okay, so therefore this cannot be a vector space. Okay, and the beauty is this R over R has only one subspace, that is zero subspace. If you look for a proper of course this this is called improper subspace only. But if you look for a subspace subset of R, which is a subspace, that is nothing but zero subspace only. There are no other subspaces. You can verify it. Okay, why? Because field itself is a big. So you can't take the vector set to be smaller than the field. Okay, and the other one. So let me discuss about R2. V equal to R2. R2 over R only. All right. Now, what are the possible subspaces of this R2? I hope you can see the picture of R2. X here and Y here, and you know how to represent elements in R2. 1, 2, 3. 1, 2, 3. Right? And whereas the negative numbers here. All right. So can you give me a subset of this R2, which becomes a vector space? U, which is a subset of R2. And I hope the first example you give me is this. It means the set which contains only zero elements, 0, 0. That you can simply write it like this, 0 bar. Right? So definitely this becomes a vector space. There is no doubt in it. So other than zero subset, give me some other subset. And remember one thing, అది subspace అవ్వాలంటే vector space అవ్వాలి. Vector space అవ్వాలంటే 0, 0 అనే ఎలిమెంట్ కంపల్సరీ ఆ సెట్లో ఉండాలండి. అంటే మీరు ఏ సబ్సెట్ తీసుకున్నా సరే దాంట్లో ఈ ఎలిమెంట్ 0, 0 ఇంక్లూడ్ అయ్యేటట్టే తీసుకోండి. ఒకవేళ ఆ సెట్లో 0, 0 లేదనుకోండి, స్ట్రైట్ ఫార్వర్డ్ వీ కెన్ సే ఇట్ ఈస్ నాట్ ఎ వెక్టర్, ఇట్ ఈస్ నాట్ ఎ సబ్ స్పేస్. Set of all points on the x-axis. Very good. So how to write that set? This is how we can write set of all x comma 0 such that x belongs to real numbers. So it is nothing but the x-axis itself, right? So adding two elements on the x-axis, it is there again, and multiplying an element with a constant, it is there on the x-axis. Therefore, it is very clear that it is a subspace of R2 over R. Can you give me one more? All right. So here there is one more, that is x comma x square. Interesting. So if I take, um, so the third example is u equal to, it is given x comma x square such that x belongs to real numbers. Right. I appreciate this example. Why? Because I asked you to take a set which contains zero vector. Right. Yeah, definitely this set contains zero vector. There is no doubt in it. But the problem is, does it have a vector space structure? So this set is nothing but, this is the graph of y equal to x square, isn't it? Set of all points on the parabola. Now the question is, if you take 2 points on the parabola, if you add it, the result, will it be there on the parabola? Okay. Anyway, why to use big words? Let me take two elements here. 1 comma 1 is an element of u. All right. And similarly 2 comma 2 square, that is 4, that is also an element of u. But how about their addition, that is 1 comma 1 plus 2 comma 4, which is nothing but 1 plus 2, that is 3, and 1 plus 4, that is 5. But you can see that this 5 cannot be written as 3 square. Why? Because 3 square is actually 9. ఈ సెట్లో ఏ ఎలిమెంట్ అని ఉండాలంటే ఎట్లా ఉండాలండి, ఇక్కడ ఏదైతే తీసుకున్నారో దాని స్క్వేర్ అనేది సెకండ్ ఎలిమెంట్గా ఉండాలి. ఇక్కడ ఫస్ట్ ఎలిమెంట్ 3 ఉంది, దాని స్క్వేర్ ఏంటి 9 ఉండాలి. ఇక్కడ 9 ఉంటే ఐ సే దట్ దిస్ బిలాంగ్స్ టు ద సెట్. బట్ వీ డోంట్ హ్యావ్ 9 హియర్, సో దేర్ ఫోర్ యూ కెన్ సే దట్ విచ్ డజంట్ బిలాంగ్స్ టు యూ. So adding two elements here does not belongs to the same set. Therefore, it is a subset, but this is not a subspace. Right. I appreciate this example. Why? Because if you don't see it here, you would have seen it in the exam. It's not a subspace of V over R. Y equal to, okay. Another example is x comma mx plus c. All right. So let me write one more. So u equal to, it means you're considering almost all lines, right? So x comma mx plus c such that x belongs to real numbers, right? But if you take it, I'm asking you to take a set which includes zero element, right? When 0 comma 0 is included here, in which case 0 comma 0 is included, what is the condition on m and c? Yeah. When c is 0, then only 0 comma 0 is available here. Otherwise, if I plug in x equal to 0, then you'll have 0 comma c. It means, see, the example what he gave here is set of all lines. If the moment you say mx plus c, suppose if m is a fixed quantity, c is a fixed quantity, that is just one line. Suppose if you vary m and c, that represents set of all lines. Okay. Okay, so let us take one such line. So let me fix m and c. So by fixing m and c, I may get some line like this, provided the slope is negative and the y-intercept is positive. Suppose if the slope is positive and y-intercept is negative, you would have seen the graph like this. Okay, but these two are not passing through origin. When the y-intercept is strictly positive or y-intercept is strictly negative, definitely it is not passing through origin. So this line passes through origin only when the y-intercept is 0. Okay, it means c has to be 0. So now we can take this example, but with a small modification. The modification is, so u equal to set of all x comma mx, x comma mx, such that x belongs to real numbers. All right, where m is a fixed quantity. So let me name it as um. M is a fixed quantity. You can take 1, 2, 3, 4, 0, anything. If I take 1, that represents x comma x, that is y equal to x line. If I take m equal to 2, that represents y equal to 2x line. Right? Now we can see that this creates a vector space. 0, 0 element is present here. And you take two elements. Let me take x comma mx. Okay, let me name it as v1 and v2. That is what some not alpha. Let me use x1 here. So x2 comma mx2. If I add v1 and v2, you can see that the result is nothing but x1 plus x2, and here you'll get mx1 plus mx2, but m can be taken out, so m into x1 plus x2. So finally, whatever you have it here as a first coordinate, so the second coordinate is a multiple of the first coordinate multiplied by m, right? That is what they said, right? So we are very clear that this element belongs to um. All right. So addition is fine. Now let me look at the multiplication, that is alpha into v. So that is alpha into x comma mx, and which can be written as alpha x comma m into alpha x. Right? Yeah, whatever you have it in the first coordinate, the second coordinate is multiplied with m. Right? So now definitely this belongs to um. Therefore, addition is fine, scalar multiplication is fine, and rest of the properties anyway follows from the bigger set. Why? Because in the bigger set all those properties are true, so in the smaller set also true. I'm talking about associativity, commutativity. Okay, but additive identity, additive inverse, you need to make sure additive identity is anyway there. But you know, the beauty is, if it satisfies these two property, additive identity will be there definitely. There is no doubt in it. Why? Because here you take one element as v, another element as minus v. If v is there, like if these two conditions are satisfied, if v is there, minus 1 into v is also there. Now if you add these two things, what is it? It will give you a zero vector. So zero vector is there. So if these two conditions are satisfied, implies that zero element is available, and also additive identity is also available, because for every v I just multiply with minus 1, so that becomes minus v. And you know that for every v, alpha v is there in that big that subset. Are you getting it? అంటే సబ్స్పేసా కాదా అని చెక్ చేయడానికి ఈ రెండు ప్రాపర్టీస్ చెక్ చేస్తే సరిపోతుందమ్మా. All right. And one more beautiful thing about this R2 is the set of all subspaces of R2 are nothing but lines passing through origin. All lines passing through origin. Those are the subspaces of R2. And one more subspace is zero space. Other than zero space, the other spaces are nothing but set of all lines passing through origin. మీరు R2లో ఏ సబ్స్పేస్ తీసుకున్నా సరే అది దట్ మస్ట్ బి ఎ లైన్. ఇంకా క్వాడ్రాటిక్ కర్వ్స్ ఏం రావండి ఇక్కడ, క్వాడ్రాటిక్ అని క్యూబిక్ అని రావు, ఛాన్స్ లేదు. ఓకే, that must be a line passing through origin. And the fourth example, which gives you all subspaces of R2. Okay, so this is a beautiful example. All right. Now I request you one thing. You think about what are all subspaces of R3? R3 over R. Okay, so in R2, we said those are lines. The proper subspaces are lines passing through origin. Now you are in a three-dimensional space. Okay, now the question, the line passing through origin, can it be a subspace here? And the plane passing through origin, can it be a subspace here? Right? After verifying these two, and you think, are there any subspaces available or not? Okay, so I'll do one thing here. I'll give you some exercises. With that, I'll stop. So W equal to set of all x comma y comma x plus y, such that x y belongs to real numbers. Try to understand, this is a triple. When it is a triple, it means it is an element of R3. So it is very clear that this is a subset of R3. Now the question is W over R a subspace of R3 over R? Okay, and similarly I'll give you one more. W equal to set of all x x y, and that's the second component y తీసుకోవాలి కదా అనొచ్చు. ఫైన్, నేను x తీసుకున్నా, then ఇక్కడ y తీసుకున్నా. don't see that as an y component x component. లేదు మీకు x yలు ప్రాబ్లం అనుకుంటే I'll write alpha beta alpha beta, but alpha we are using it for elements in the field, so I don't like to use them. ABC use చేస్తా, అది better. A B, where a comma b are coming from real numbers. This is clearly subset of R3. Now the same question, is it a subspace? And the third one, W equal to, now I'll jump to polynomials. One no, let me take like this: a plus bx plus cx square. This is a polynomial such that a plus c equal to 0, where I'm taking this a comma b comma c, I'm taking these from real numbers. Okay, now it is clearly a subset of P2. It means set of all polynomials of degree less than or equal to 2. Now the question is it a subspace of P2? Okay, so not only this, I'm going to share one assignment sheet. You please try to think of them, whether are they subspaces of the big vector space or not. All right, here I got few more examples. X square plus y square equal to 1. That is a circle. Moreover, unit circle. But is 0 comma 0 available in that set? The problem is 0 comma 0 is not available. అది ఫస్ట్ వెక్టార్ స్పేస్ అవ్వాలంటే 0 ఎలిమెంట్ ఉండాలండి దాంట్లో. అక్కడ 0 ఎలిమెంట్ అవైలబుల్ లేదు, దేర్ఫోర్ ఇట్ కెనాట్ బి ఎ వెక్టార్ స్పేస్. కానీ ఆ యూనిట్ సర్కిల్ కి బ్యూటిఫుల్ ప్రాపర్టీ ఏంటంటే, అక్కడ మీరు 2 ఎలిమెంట్స్ యాడ్ చేస్తే మళ్ళీ యూనిట్ సర్కిల్ పైన రాదు. బట్ when you multiply 2 elements on a unit circle, the result will stay on the unit circle. యూనిట్ సర్కిల్ మీద ఎలిమెంట్ ని సమ్ కాన్స్టెంట్ తో మల్టిప్లై చేయమంటలేను. యూనిట్ సర్కిల్ పైన 2 పాయింట్స్ తీసుకోండి. ఆ 2 పాయింట్స్ ని మల్టిప్లై చేస్తే ఆ వచ్చే రిజల్ట్ కూడా మళ్ళీ యూనిట్ సర్కిల్ పైన ఉంటుంది. దట్ ఈస్ ద బ్యూటీ అబౌట్ దట్ యూనిట్ సర్కిల్. బట్ ఇక్కడ వెక్టార్ స్పేస్ స్ట్రక్చర్ అయితే అక్కడ లేదు. All right. So with this, I'll stop. And let me know if you have any questions or doubts.